Okay, so welcome everyone. My name is Ana Maria Farsakoglu. I work for the EUFORGEN Secretariat and for the OptFOREST project. And I would like to welcome you to the first EUFORGEN webinar in the EUFORGEN webinar series for 2025. Today we're going to talk about the mechanisms of natural and anthropogenic selection on trees in the forest. And we have with us François Lefèvre. François will be the speaker of this webinar. He's a geneticist at INRAE, France, and he's based in the Mediterranean Forest Ecology Research Unit in Avignon. François serves as the president of the French Commission of Forest Genetic Resources, and he has also been for years the national coordinator for France in the EUFORGEN program. Also, he is a work package leader in the OptFORESTS project. His background is quantitative and population genetics, and he led interdisciplinary research focusing on the impacts of forest management on both the short-term performance and long-term adaptive capacity of forests in the context of climate change within a broader framework of social and ecological approaches. So without further ado, I would like to give the floor to François. And François, you can share your screen and you can start your presentation.
Okay, thank you. Can you see the?
Yes, we can see it perfect.
Okay, so many thanks and thank you, EUFORGEN, for with this organization of this webinar to give us the opportunity to share with you what we learned, the knowledge on natural and anthropogenic selection on trees in the recent years. So we prepared this presentation with Victor Fréron, but other people were involved in this research for several years now, and I want to mention them, and they are associated with this presentation definitely. Claire Godino, Sylvie Odou-Muratorio, Hendrik Davy, François Courbet, Nicolas Bedez, François de Coligny, Gauthier Ligaud, and Leopoldo Sanchez. And also we had the benefit from fruitful discussions with participants of an INRAE network about demogenetic agent-based modeling. So I will explain you what it is about. And this research was funded by national funds, INRAE, which is a multi-actor platform, the French Forest Service, and two EU-funded projects. Currently, OptFORESTS is funding this research, and BFOREST before. So this is the plan of the talk. First, an introduction to put the issue of selection in a context and propose a simple conceptual framework that will help to follow the presentation afterwards. Then in a second part, I will briefly review what evidence we have that selection is ongoing on trees in the forest. And then third part is the main part is the model-based approach that we developed to understand the mechanisms of selection and explore the impacts of forest management scenarios, and then conclude with some lessons learned for climate change adaptation strategies and perspectives. So to put a bit of context, we all know these kind of graphs from the IPCC with temporal horizon generally until 2100. And then we know that trees have a specificity of being long life organisms. That means that even without climate change, they have to they are submitted to annual fluctuations of the climate. They are also submitted to disturbances, and already there, selection plays a role because trees have to survive all these events anyway. And now that climate change is coming, so there is a trend in the climate. Annual fluctuations will still be there. Disturbance regime will shift, and there are a lot of uncertainties. So now, if we add on this temporal scheme, the forest temporal horizon, this is the one. So here I just represented two types of cycles, a long one, which is a bit less than 200 years cycle, and a shorter one. But yes, this is what we are talking about. Forest temporal horizon is 2 to 5 generations of trees, not hundreds of generations, and it is more than 100 of years actually. So in this temporal horizon, selection, I call it also an ecological process, not only evolutionary. Ecological is what selection does within one generation, during the cycle. All the from the seedlings to the end of the cycle, the bad individuals are removed by selection, so there is a change in the capacity of the forest, continuous change. So selection is an ecological process that shapes the capacities of the forest. And then, of course, it's also an evolutionary process from one generation to the next. What we know also is that trees, they have more genetic diversity than other organisms. I will not develop that, but this is a fact now, and they have a high potential response to selection. And also what we can see from this forest temporal horizon is that any management intervention, whether it be for short-term or for long-term objectives, it will have always both short-term and long-term impacts. So it is very important to have that in mind. Well, of course, selection and adaptation is not unlimited, and it will not solve everything. So we have these obvious limits. You have on the top right the distribution range of one species, silver fir in Europe. In green, you have the natural range, and in orange, you have the use range. And well, you cannot put these species everywhere, so it has some limit. The top figure, it's a mountain, Mont Ventoux, south of France. And you see from these colors that different species have different altitudinal range. So that means they are not able to be everywhere. So there is a limit. And at the bottom, you have these terrible bark beetle attacks here in the northeast of France. Well, obviously, this population is completely collapsed. And you have on the left the evolution of the big damages in millions of cubic meters during the last 50 years in Europe. And you see with such big events, in yellow you have the winds, you have the bark beetle, you also have the fires and other events. With such big events, selection cannot do much. So selection cannot solve everything, and definitely the possibility of adaptation by selection should not be an excuse for climate inaction. So climate change mitigation is the priority, but forests can contribute to climate change mitigation if they adapt. So there is a dependency of mitigation to adaptation and selection, and vice versa. Forest adaptation is possible only if there is climate change mitigation in many areas. The point is that selection and the capacity of adaptation behind is very often overlooked, and its role in ecological and evolutionary role of selection is overlooked, and I hope I will convince you about that. Another point also to put our minds here is to consider that trees are long-lived sessile organisms. So every year they are submitted to different pressures of selection. What you have on these graphs on the left is the monitoring of mortality every year in a nature reserve in La Massane. It's a beech forest in south of France. And every year they record the individual tree mortality. You have the orange curve is the evolution of this annual mortality from 2004 to 2016. For the same years, we used ecological model and climatic data to estimate what was the risk given the annual climate of different mortality causes. On the top graph, you have mortality by cavitation, and this happens when there is severe drought years. On the second from the top graph, you have the mortality by carbon starvation, and this happens when you have long drought periods. And the third from the top is a frost event. You see that each of these causes explain only part of the annual mortality pattern, and it is only on the bottom graph where we made a composite index that we start to understand what is the pattern of mortality, of annual mortality. What does it mean? It means that there are multiple successive mortality causes across years. Okay, so selection is dynamic. It's not always the same. Every year selection changes. It's multidimensional, and it is stepwise. Stepwise means that the trees that are submitted to frost, for example, have been submitted previously to drought. So only those that survive to drought can try to survive to frost afterwards and so on. So then this gives us a new definition of what is a tree. A tree, a living tree, is a multi-skilled survivor. This is a definition you can give of a tree. So now we need to have a bit of theoretical framework to help understand selection. And this is a basic framework. You can have others more complex, but this is the so-called breeder's equation that was defined earlier in the 20th century. And it considers that selection occurs in two steps. The first step, when you start from a population, you select the parents. And the second step is that there is mating of selected parents. What you have on these graphs is the different steps. It shows the distribution of a trait, the trait which is the direct target of selection. This is a breeder's equation. The breeder is selecting on a particular trait. So you have on the top the distribution of the trait before selection, and the breeders select only the green part of the distribution. So after selection, you have a new distribution in the selected parents, and this is so-called the selection differential, is the difference of the mean of the initial population and the sub-population of selected parents. And then these parents, they mate, and because what makes the difference in the parent is not only the genotype, it's the phenotype, but they only transmit the genes to their offspring. Then in the next generation after mating, the progenies of the selected parents are not exactly like the parents, and they come back to the initial distribution, let's say. So, and the genetic change actually is the product of the selection differential by the heritability, which can be written also in three terms by the product of selection intensity. Selection intensity is how much you derive the selection differential, the heritability, or the square root of the heritability, and the standard genetic deviation. Okay, the higher intensity, the higher genetic change, the higher heritability, the higher genetic change, and the higher initial variance, the higher genetic change, because you go further. But this is good for breeding when you have the direct target of selection. But in nature, natural selection only has one target, which is the so-called fitness. And then we need to derive the same approach with what we call indirect selection. It is the fact that you select on a trait, here called W, which is the classical letter used for fitness, and you look at what is the selection on another trait that is correlated to fitness. And you see the formula is a bit different. You also have the intensity of selection on fitness, the heritability, but you have these correlation terms. So when you look at the results of selection, natural selection acts on fitness, but you look at the result on a trait, and the result of selection on a trait depends on this correlation between the trait and the fitness. And this leads us to have this link, this chain diagram from fitness, which is on the right, this red star, back to the genes. And you see that what makes the link between the genes and the fitness is a very complex thing that goes through, you go from the space of genes to the space of traits and syndromes of traits, combinations of traits, and then the fitness components and the fitness. And you have a chain like this. And all these links make the correlation between the fitness and what you are looking at when you are looking at the result of selection. In the space of traits, here I represented different types of traits in a hierarchical structure. Actually, it could be even more complex, but you have on the right the so-called integrated traits. Let's take an example. An integrated trait could be, for example, frost resistance. But frost resistance is linked to a physiological function, which is phenology. So you have integrated traits would be frost resistance, and the phenology would be the physiological function. But phenology can also serve another integrated trait, which is drought resistance, because phenology can lead to drought avoidance. So you see that a functional trait can have impacts on different integrated traits, okay? And what is the basic trait of phenology? Because phenology, you know, there are different parameters, which are the chilling or forcing requirements, temperatures, and these are the basic traits. In general, basic traits are the ecophysiological. So this is important. All these links, they are dynamics. They vary through time. This is the small t, and they also vary with the environment. Okay, if in a cold environment, there is a link, of course, with phenology and fitness, but in some other places, the link between phenology and fitness is much smaller. And this gives a kind of elasticity to the consequence of selection. Natural selection only knows fitness. So, considering selection in forest trees as a dynamic process and continuously changing, here are the questions. What are the drivers of the dynamics of selection? What are the successive steps that creates this selection differential that will only keep some individual trees remaining for reproduction? The second question is, what is the potential evolutionary rate of adaptive traits in forest trees, given the speed of climate change? For example, is it possible that they evolve quick enough? The third question is, how can forest management accelerate or slow down selection towards adaptation? And there is also another point I will just briefly address. How fast does selection erode the potential of future evolution? So what evidence do we have on ongoing selection processes? We have different types of empirical evidence. One type is illustrated in this study by Alexandre et al. On oak forest in France. In this study, there are two oak species coexisting, and they studied multiple successive generations of trees, the parental and the next generation. They developed a methodology to estimate, looking at roughly who are the parents of the second generation, looking in the first generation, what was the reproductive success of the parents in the previous generation, in the parental generation. This is the reproductive success is an estimate of the relative fitness. They could estimate relative fitness in the first generation. So for selection to occur, there needs to be variation in the relative fitness of the parents. And this is the graph on the left that you see, okay, all the parents do not have the same fitness. That means there is selection for the parents having the highest fitness. So selection operates. And on the right, you have the number of traits that show in the parental generation a correlation with the fitness. So this correlation term, indirect, so it gives in this table how many traits have significant correlation to fitness when it appears in red. So for example, for Quercus petrea, growth traits, there were 4 growth traits, and all of them were correlated to fitness. There were 6 traits related to phenology, but none of them was correlated to fitness. That means that none of these phenological traits were submitted to selection, probably. Okay, and physiology, there were 3 out of 7. And you see resilience, there were 3 parameters. None of them was correlated to fitness, so there is no selection on this trait, apparently, and this and so on. So you see, there is selection potentially operating on these traits. And from one species to the other, in the same forest, you have different traits and different selection pressure. Another type of evidence is from microgeographic adaptation. That is in very short term. So what you see here on the left is a Mont Ventoux slope from the top to the bottom. It's about from 100 and 400 meters in the top to the bottom, 900 meters here. And 150 years ago, mid-19th century, there was almost no more forest there. So there was a local recolonization in 150 years along a gradient of 3.5 degrees, which is more or less what we talk about when we talk about climate change. And today, if we take progenies at different levels, the progenies have different, if we put them in common garden conditions, they have different genetic capacities. You see on this graph, growth capacities are different, and also bud burst dates, phenology is different. That means that despite a large amount of gene flow through pollen flow at this scale, there is already local microgeographic adaptation that occurred very rapidly. Along this gradient in one of these slides, this is what we see. In this mixture of beech and fir, what you see in the beech, you have 2 different types of individuals. Some have already flushed, and others are already with the bud closed. So there is a bimodal distribution in flushing dates in the same place. And what we could see by studying also correlation between traits is if we consider the growth as a proxy of fitness components, it is one of the so-called vital rates in the complex graph I showed before. It's very much related to fitness. Well, there are two different optimum so-called trait syndromes, which are combination of traits. Either you have early flushing individuals. Actually, they are advantageous here. It's an advantageous strategy because they they make most of their growth before the dry season occurs, okay? But there is a risk is that they are taken by late frost. But so those trees, they can be winners if they grow very fast at the early season. Another type of winners, they are later, they avoid the frost risk, but they grow more slowly in the beginning, but they continue growing in the dry season, and they are more adapted, they are smaller vessels and so on. And you have here this vision that the two combinations are possible and coexist. This is really important to have in mind, that selection is not a selection for a unique optimum, is very often selection for multiple optimum strategies in a local site. So another type of evidence we have is at the gene level. Here it was a study by Scotty et al. On 4 conifer tree species in Europe. And what they did here is to sample in different forests, in each case, 2 different sites within the same forest in good and bad conditions. You have the illustration here in the same forest, the good conditions on the left and the bad on the right, and the trees have the same age. And these twins sampled were taken for different different forests for each species, and they made genomic analysis using SNPs, and they looked at the SNPs if there were any genes that were significantly differentiated between the sites within each forest. Okay, it's the between sites within each forest. So, and you have these so-called outlier SNPs, and for each species, they found some significant SNPs. So there are genes that respond to this very local adaptation. And this is very strong local selection, actually. And you have the violin graph represents the estimate of scaled selection intensity. We can have figures on that on each of these outlier genes, 0 being neutral, so no selection intensity. And the final case, so we have studies across generations. We have microgeographic adaptation that shows that there is continuous selection operating. And the other kind of evidence we have comes from introduced species. Here you have the case of introduction of cedrus in France. It was introduced in the late 19th century to restore over eroded areas. You have this aerial picture on the left, top left, and this is the surviving trees after this initial plantation in very, very terrible conditions, not suited for the species, and very few survivors. But these survivors, they progressively developed a forest, and now you have this picture on the bottom right, which is the current situation, very dense forest. So through time, the first generation of trees, they had to survive to very harsh conditions and dry conditions. But now the young generation, they have to survive to competition, actually. And there is, from one generation to, there are 3 generations here represented. 3 generations of trees. From one generation to the next 2, there is a shift in the selection pressure, drought resistance, and rather competition. And what we see is here on this graph is that there is a change in plasticity. So this is represented the radial growth, the pattern of radial growth with age in different conditions, predicted in different conditions, in dry conditions on the left and in good conditions with water in summer on the right. And what we see is that the younger generation takes more benefit of the good years than the older generation. There is a shift here. And final example, this is a classical example of spruce in Norway. So spruce were introduced from Germany and Austria to Norway. And of course, when they arrive there is the problem of frost. And these original trees that were planted there were severely damaged because their phenology was not locally adapted. And you see here the bud set date. These 2 original populations from Germany and Austria, they closed their buds very late compared to the local Norwegian population in green. But the striking fact is that the progenies of these introduced provenances behaved just 1 generation after. The progenies obtained in Norway, they behave just like the local resources. In 1 generation, there is a shift. Look, it's more than 2, almost 3 weeks of phenology difference between the parents and the offspring. So there is a drastic shift in 1 generation. So in this case, epigenetics is likely also to contribute to rapid adaptation. So there is in trees a huge amount of variability, a capacity of response to selection, and there is selection occurring. So the question is, why is there still a huge genetic diversity? Why do we not have lost all the diversity? So there are many reasons for that. First, because adaptation can also occur through plasticity and acclimation, so without changing the genetic diversity. Also, the inheritance mechanisms and short-term adaptation and short-term selection, I will come back to that afterwards, acts more on a combination of genes rather than on individual genes. And then it keeps the variation of genes here. So there is selection without rapid erosion. Then you can have also, like on this picture, multiple adaptive syndromes. Here, there is no 1 single unique, there are 2 optimum situations. Also, selection varies in space, and there is gene flow, so this brings in always new genetic variation. Selection varies through time. We've seen that in Lamasan. Selection varies with age. There are also coevolution mechanisms. In small stands, there can be stochastic genetic drift in small stands. There is epigenetics and mutation. So there are many reasons why, despite selection, there is not so much loss of genetic diversity. This is crucial. So the model-based approach now to study, understand selection mechanisms. So I have to speed up a little, sorry. So we use here a demogenetic agent-based modeling approach. What does it mean? It can be defined, it's an individual-based population dynamics model with heritable trait variation, and where the interactions between individuals depend on the phenotype. Okay, in this approach, selection is not predetermined. It is an emerging process that emerges from the population dynamics, from the interaction among individuals, and therefore from individual variability and from the heredity. Okay, so here you have a comparison of this approach on the right and analytical models. Here we are here doing at individual level. Population dynamics is not uniform. Within population, variation can be whatever. It is distribution free. Inter-individual interactions here, there will be explicitly modeled. It can be competition, it can be reproduction, it can be others. The trait to fitness relationship, which is important, this is also an emerging flexible property of the model. It's not a predetermined thing. And management practice can be at individual level. So the model we developed here on trees is this. What it is. In green, you have the combination of a classical forest dynamic model, a growth model, where growth, survival, and reproduction is modeled, with genetic diversity. And there is feedback on this. So growth, survival, reproduction will drive competition and genetic diversity, which in turn will change the growth potential and survival potential and so on. This is the loop. But on this system, on the left, you have an initial situation, of course, and the genetic background of the initial forest. And on the top, you have silviculture and disturbances. So here, I will talk of disturbances called due to drought stress. And drought stress is the combination of an external hazard, which is the climate, with the stress depends also on the population dynamics, because the drought stress depends on the leaf area index, which dynamically relates to the forest dynamics. Okay, so drought stress is a combination of external and internal process. It is an eco-evolutionary. And then, having all this, we look at the functional and evolutionary response of the system. If you remember the four terms of the response to selection in the Breeder's equation, the selection intensity, this is an emerging property of the system. The heritability is an input. The initial genetic variance, it's an input, but then it evolves by the system. And the correlation between the traits and fitness is an emerging property. They are not predetermined. So what happened in a forest? There are two types, two families of mechanisms of selection. On the left, you have, let's say, selection by competition, which is a density-dependent soft selection. That means that a tree, any kind of selection where a tree is selected because it is relatively better than another one around. Okay, this is one type. The other type of selection is hard selection on individual characteristics independently of the others. Okay, here you have, typically these are, here it is drought resistance. So some trees are capable to survive, other, whatever is are the others. So now, what does it mean? If we represent here for competition, this is a forest, so as thousands of lines that represent the individual tree growth through years. And when a tree dies, the line stops and its name appears in black. Okay, and at the end we cut the tree, so they are all dead. So what happens is that all trees are of different size, and the dominant trees are the ones that survive. So progressively, when the mortality the mortality occurs, every year the vitality or the growth potential of the remaining trees increases. Okay, the population every year change the composition and the capacity. Okay, so the dominant trees, they survive longer, and at the end they also contribute more to the regeneration. Now, what happens if there is disturbance on individual characteristics? So here, what happens? There is stress. So you see some years like here, you have a year with a drought event, a lot of mortality, another one here, another one here, another one here, and in between some years where just a few individuals die. But still, what does it? It has an impact also on the competition, because by killing trees, it reduces competition. So it relaxes the other type of selection. There is a feedback between the two types of selection. Okay, and also it does not completely remove the selection by competition. You see here there is still movement of selection by competition. So what did we do in our model? What kind of variability did we introduce? We introduced variability on two traits you have here on the left, which we call vigor and drought sensitivity. On the left, you see two trees, A and B, and what is represented is the annual growth of these trees, depending on the drought stress level. So A is growing better than B when there is no stress or when the stress is low. But because A is more sensitive to drought stress, then when there is a high stress, B is growing better than A. So this happens every year. So in good years, A goes better, but in bad years, B goes better. So at the end, what happens? It depends also on the accumulation of the different years. And there is a system where if the growth reduction is too high, there is mortality of these trees. If I come back to this complex link map that I presented before, this is a simplified version actually. We only have here what could be called integrated traits, which are sensitivity and vigor, and directly genes connect to sensitivity. We make a black box with all intermediate traits. And there is environmental effect and also temporal effect that change the link of between genes and sensitivity. And this vigor acts on growth, that will drive survival on the competition and drive reproduction capacity, which will drive natural selection. Sensitivity will change also the growth, and it can act also at the end directly on survival. Okay, so you see the link, and of course there is a fitness at the end. Natural selection operates on fitness, and what we add also is that there is the forester, and the forester can make thinnings, and when he makes thinnings, he kills trees, and he chooses the one that he kills, and this makes a selective selection here, which is another one. So now the point was, how can we vigor and sensitivity, can we calibrate the variation that we have for these traits? So we did this work for 5 species in France in ICP level 2 network forest. So what you have on the top left is the graph that defines the classical growth model for its species. And this is a family of model, which is the blue curve. And when this model is fit on the data, then you have residuals, and vigor is the individual variation around the model, and this is the vigor. And then you have on the slide, we define the sensitivity as the reduction of the potential growth when there is a drought stress. So to estimate these values, we used dendrochronological data to have the pattern of annual growth. We used climate and soil data with an ecophysiological model to study the past recent history drought stress correlated to growth patterns of these 5 species. And we obtained this kind of figures. On the left, you have for Douglas fir in 3 different stands, the variation in vigor in X and in Y, the individual variation in sensitivity that we estimate. And very often we have a trade-off here that it means a positive correlation between vigor. The more vigorous trees are also the most sensitive. This happens in many cases, but not in all, actually. And if we put all the species together, this trade-off can be explained by selection. And actually, if you remove those individuals that are not vigorous and are highly sensitive, then you have, selection creates a trade-off. And here you see that this correlation, the trade-off, is more important when the available water in the soil is low. That means that in more selective sites, you have a higher trade-off correlation. So using all this in the model, I will go rapidly now because I'm late, sorry for that. We could estimate evolutionary rates without any management and through 3 to 4 generations of trees. And the evolutionary rate is measured in the amount of initial phenotypic variation, the amount of change per generation in the unit of the initial standard variation of the trait. And our estimate for the 2 traits, vigor and sensitivity, was around 0.6. And we don't have empirical estimates of these evolutionary rates in trees because it requires to have multiple generation data sets we don't have in trees. But we have that in other plants. And this is a review of evolutionary rates estimated empirically in different plants. And we fit in the figures. So now we can look at what are the impacts of management. Here we just want to study the effect of selection by competition without disturbance. And we proceed just by making neutral thinning, so without choice of the trees, that suppress competition. And we look at here on the bottom right, the evolution of the genetic mean of vigor, which is there is no stress, so there is no selection on sensitivity in that case, across years. Here there are 4 cycles, 4 generations. In green, you have in free evolution, so with competition, and in red, you have we make this thinning that suppresses competition. So if there is no competition, there is no selection on vigor, except at the time of reproduction, because this is fecundity selection. This is the fact that bigger trees, they still contribute more to the next generation. So there is this, but only this. And while in the green free evolution, you have both the selection differential year through year, and then in addition, you have the fecundity selection. So you see the difference. Then we sometimes hear that shortening rotations may increase the evolutionary rate or speed up evolution. Well, this is not always the case. It can be seen here. If there is, here on the red, you have a long cycle or short cycle in a shorter cycle, as you can see, If you do that without competition, of course, the only selection effect comes from the reproduction event. So if you reduce rotation in a certain given of time, you increase the number of reproduction, so you increase the number of selection events, so you increase the evolution, that's right. But when there is competition, in that case, you see that the long cycle is very often with a higher evolutionary rate, because when you reduce the rotation time, then you reduce the capacity of selection to occur during the growth of the forest. Now, what happens when there is drought stress? So we apply drought stress and silviculture, which consists in selective thinning. So the forester cuts trees that are chosen. What happens in this case? In this case, silviculture is made to reduce competition and reduce drought stress. Okay, this is the objective. And of course, when doing that, what you do, you also reduce natural selection. So what you win by reducing the stress and the competition, you lose it by having less adaptation. But the forester is not making a neutral thinning, he is making selective thinning. So he creates an anthropogenic selection. So depending on how, what is the frequency, the intensity, and how the trees are chosen at each thinning, the forester can go in the same direction as natural selection, even go further, or can go in the opposite direction or slow down the impact of selection and adaptation. So the result on that is given here. So we just, because it's too late, we'll click only on the bottom right graph, which is the reduction in 3 generations of the mean genetic sensitivity. We want, of course, to reduce the sensitivity. And you see in black is the free evolution scenario, so it's natural selection alone that reduces the sensitivity, okay? In blue, you have the current silviculture, actually, which reduces even more the sensitivity. And in green, it's a deviation to the current silviculture, aiming to reduce stress by reducing density. Okay, this is the objective, reduce density. Actually, in that case, it's we obtain a counterintuitive result, is that by reducing the stress, we reduce the genetic improvement against sensitivity. So actually, we reduce less, you see, the sensitivity than the current. And in orange, it is the idea to leave room for initial selection by stress in the juvenile stage. At this stage, the forester can lose trees because it's not too expensive. They are not very valuable. And afterwards, when this selection is done, then there is reduction of stress. Okay, there are successive steps. In that case, we show that we can have a silviculture that very much improves the sensitivity. And you have the same evolution in vigor. Of course, for the forester, it's not the issue because the forester has no money from the mean genetic value. So what means for the forester is here on the left is the mean diameter of the trees at the end of rotation. And first rotation, the second rotation, and the third rotation. You see in black, there is the free evolution. So in all cases, of course, having a silviculture and thinning improves the mean diameter of the trees. Okay, this is done for that. In blue, you see the current situation. And in green, there is the reduction stress strategy, which is good for the first rotation. Okay, in the short term, it's good. It's the best one. But already in the second run, it's not the best one. And in the third, we could do better than this. Okay, so I will end with some lessons learned for climate change adaptation strategy. First is selection on trees. It's a continuous dynamic process contributing to forest resilience. I will not develop this, but this is a conceptual framework by Siddle and Turner about the adaptive cycle, and selection will really is a key process on what will happen in this adaptive cycle of the forest after a regime shift in disturbance. The second point is that neglecting the role of individual variability and selection can lead to non-optimal decisions. Like, for example, reduction of stress only is not always, in some cases it's the best, but not always, it's not always the best option. And forest management can act both on the variability and on the selection process itself. And this is the framework that we developed some years ago about evolution-oriented forestry, and we have how we can think that a link between forestry practices and the drivers of genetic diversity and adaptations. So from this, we now have first estimates of potential evolutionary rates and of the impact of forestry practice on integrated adaptive traits. Another lesson is that there is no universal solution. All the impact of solution depends on the environment. So adaptive management strategies must consider the local context and the local condition. You do not behave the same if you are in a highly stressed or non-stressed area. In adaptive management strategies for uncertain future, natural selection is not an enemy. It can be an ally, because we don't know exactly what will be the key driver of future adaptation. Maybe an emerging text, and natural selection can help us from that. Genetic diversity is a resource for management. That means that conservation and sustainable use of genetic resources is an issue in all types of forests. Not only very often forest genetic resources are considered as useful only for plantation forests. No, they are useful for all types of forests, including in natural regeneration systems. And forest managers must realize that they are also act as tree breeders somewhere, and they are also curators of genetic resources. Yeah, and just a few words of current work in progress, in particular in the OptFOREST. We now introduce non-stationary drought regimes in the model to explore also management options in declining stands. We will explore assisted gene flow strategies with this kind of approach. And we will add some biotic disturbance regime to explore multi-risk management scenarios. And these simulators can also be very useful for teaching and training. Yeah. And thank you for your attention, and sorry for being so long.
Thank you very much, François. It was very comprehensive and it was very interesting. So I think everyone was very happy, even if it took a little bit longer. So I would like to open the floor now for some discussion and some questions. You can raise your hands or type your questions in the chat. Anyone? Okay, I have a question from Eric. Eric, please go ahead.
So thank you, François, for this very interesting talk, and that gives also room for a lot of thinking. So you mentioned about the epigenetics in the Norway spruce, the piece apis case, that the epigenetics is also an important effect. So how do you think this could be integrated into your modeling and thinking?
Definitely, it's not for the moment. Yeah, it could be, but it could be another mechanism. Well, technically, it would have to be more different. Epigenetic would be a kind of temporal memory of changing environment somewhere, this kind of thing. yeah, it could be not. It's not included. My feeling is that currently epigenetics is occurring, but we can still explain a lot of things without calling for it. So yeah, I would rather be that way.
Okay, thank you.
Thank you. Any other questions? Irina? And then Tröster?
Hello, thanks so much for your very interesting report. I would like to ask your opinion about relation, different kind of influence of mycorrhiza on the things that you explained today. Do you think that it can cause some resistance to different factors, probably also to drought? And did you study this process, that kind of relation?
Yeah, so definitely for sure, mycorrhizae play a crucial role in terms of drought resistance in particular, but more generally on adaptation of trees, that is for sure. It is not included in the approach that we have. And for the moment, the only development we are working on is about association with other organisms, is rather with parasites, okay, or insects in this case. But yes, definitely this is also, yeah, the mycorrhizae have a very crucial role to say. Then there is a question which I'm not sure about, is how far there are evidence of coevolution, for example, between trees and mycorrhizae. I'm not sure of that.
Thanks a lot.
Tröster?
Yes, thank you, François, for a very, very informative talk. And those of us here, which I assume are most of us, trained in forest genetics, understood it. But the most powerful people that you talked about are actually the people doing the thinning in the forests. And most of them are not trained in, probably none of them are trained in forest genetics. So to get this information to them and into use in managing forests is a big step, which I have been dealing with as here in Iceland. We're starting to thin our forests, and I am concerned that it's not being done in a good way. So do you have any ideas about how to get this information to the people actually doing the work?
Yes, I have. And you see, if I can share again my screen. Okay, you seen from here, I put this, and this is something I'm very engaged in currently. And just to show you some experience, these simulators, you see, it has a graphical display which is user-friendly, and you don't need to know anything about the model itself. Even I tested it here. It was what we call advanced course in Siam in Zaragoza in Spain. And these are only foresters. They don't know anything about genetics. Okay, there were even economists there, and they were playing the game. There was, so it's in French, a gentry. There were geneticists, a summer school, and here there were master students in Switzerland. They used it. And we recently made a kind of serious game, a challenge. so people could win. And really, we had gamers from, well, there were researchers, but in very different disciplines. And it works very well. And I think really it helps doing that by people making their own scenario. Either foresters, they don't know anything of genetics, or geneticists, they don't know anything of thinning, of forestry. But yeah, this is, I think, a very important tool. And you see all these graphs I've shown, I think they have good potential to pass on messages. So personally, I'm really ready to help and support anybody who wants to use it in teaching or training, and to provide. The key point is just to prepare the appropriate initial file, and then yeah, the experience. I don't know if Catherine is here, but she organized in just less than 2 weeks in advance training session for students, and she didn't know before anything of the model and anything, and yeah, it works. And I'm really ready to support any initiative in that direction.
Thank you very much. Next one is Elizabeth, and then we also have a question from the chat.
Thanks a lot, François. Long time
Nice
no
to see you.
Very, very interesting talk. I'm so happy to see the results of this study. I'm building a bit on the question on the previous question, also from the practical perspective. So, if now you have these practitioners training on these questions, on these thinning questions or natural evolution questions, what do you tell them if they then also ask, you know, how does this compare now with introducing adapted seed sources? So what is the power now? So a very basic practical question: what is the power now of this evolution versus the introduction of more adapted seed sources? So really a very basic question.
This is really a key question, and this is why we need to reach a kind of a level of quantification of this is this potential evolutionary rate, and this is, for me, it's crucial to reach that. The answer is it depends where you are, okay, because the what we call the genetic improvement, actually you have a genetic improvement in your forest, depends on the intensity of selection, and on the and also on the availability, the variability available for selection. So if you are in a place where there is already regular, for example, drought, let's say, regular drought events, there is regularly drought occurring, probably there is some selection already there. Then the question here, if possible, of course, if there is too much drought, you have to reduce the drought, because otherwise, if there is not too much, you should not completely reduce the drought, because you will reduce this genetic evolution. But then what may be limiting is the amount of variability available to feed, to fuel the selection. In that case, approaches like what we call assisted gene flow, this is, or genetic enrichment, can be a way. So to combine a part of introduction with natural regeneration. But if you are in a place where there is no drought currently, and you know, or you expect that there will be suddenly a severe drought coming in, then you can expect that locally your population is not under selection for that. And this is rather an issue, and maybe their introduction is more needed. Okay. And then I also want to react on the first part of your intervention. I am not here to say to the forest managers what they do. They ask me. For example, this idea that it's not intuitive. Currently, you have drought, you must reduce density to reduce the stress. This is the kind of message that occurs and so on. And here I come in saying, but no, not, look, if you do that, it is because you think, you forget to think about variability and about selection, so you lose something. And I propose this scheme that I showed to you that looks perfect and very nice. Okay, if you leave selection in early stage and then you reduce the stress afterwards, you win. But then the foresters came, okay, that's very nice. But in practice, if you do that, you will come probably with a situation where you leave the stand in overdense forest. And then your first thinning will be very risky. So you will have to make stepwise more thinnings to go regularly to reach the reduction of stress. So it will have an extra cost and so on. So we have this discussion. So I don't claim that we have the solution, but it's just to start discussion with them. And currently we have, so the next step in OptFOREST will be we are working tightly with them on this idea of declining forest. So actually they define the scenario they plan to use, and then we make the simulation and we readjust, they readjust and so on. So it's more exchange than one-way direction message, I think. So this kind of model is a good tool for exchanging and having people discuss.
Thanks a lot.
Thank you. We will get one more question from the chat and then we will close this webinar. So the question is, what do you think? How big is the role of biotic disturbances like pests and pathogens for selection in comparison to drought and other climate change related stresses?
Okay, so I will first part of the answer is, if I can share again, if you allow me to share again my screen. Okay, first part, do you see it? Here in this publication, all the references will be given in detail on the site where the webinar will be available afterwards. This, in the last 50 years, part of the answer, you see the damages in millions of cubic meters per year. So wind is very strong, also fire, but bark beetles because of this spruce dieback and other abiotic. So this is the first part of the answer. You had that in this very nice publication. So the other part is something that we just start now to introduce in this modeling approach some insects. The idea is, in the model, we will not introduce predetermined interactions between insect and drought to see if any interactions can emerge dynamically from the dynamics of the population. For example, if you have, you have the well-known interaction between insects and fire in Canada, for example, where you have more insect damages, you have more fuel wood for fire, and then a higher fire and so on. We will see if this approach can reproduce some emerging interference between drought and insect attacks, for example. In that case, insects will be herbivorous insects, so they can reduce the leaf area, so they can reduce the stress level, maybe. There can be this kind of interaction. Also, there is interference with competition. So yeah, we are more in this mood to study without predetermined interactions, to let interactions emerge from the population dynamics. This is the main type of research we are currently doing.
Thank you very much, François. So I think that we can close the meeting now. I would like to thank very much François and all the other colleagues that they have been working on this very nice research. And of course, I would like to thank all of you for attending this webinar today. And I wish you a great rest of the day, a great weekend. And we hope to see you all in the next EUFORGEN webinar series. Thank you very much.
Okay, thank you.